So today's topic is falling balls. It's the story of sort of the second simplest type of motion. The simplest was just coasting. So this is the first step beyond coasting. Before I start into this, about the first problem set, which is due a week from Wednesday, I will try to get it up by Wednesday. It involves authoring questions on the website, which is technically a bit tricky, and it involves other people releasing them, which is a little awkward. But anyway, that's my goal. I will try to get the problem sets up a week in advance of when they're due, so you can look at them early on, and you can come and talk to me at my office hours. The Monday afternoons, like this afternoon, I'll be in Alderman Cafe, 3 to 5, and Wednesday mornings, I'll be in my office downstairs, 9 to 11. So come and look for me. Any questions about the coasting motion, the motion of a skater who's just coasting along, the idea of inertia, that Newton's first and second laws, the first law being if you're free of forces that you move steadily, and the second law being that if you're not free of forces, if you're experiencing that force, you accelerate. Anything up? Okay. Well, so the story of falling balls is the story of a very simple motion. It's not quite the coasting motion, but it's this motion, up and down. With the ball go up and down? What's going on with that? How do we describe it? And so that's the purpose of today. And I'll start off, as usual, with this question that when I throw a ball upward, while it's in my hand, life is complicated. But once it leaves my hand and is continuing upward all by itself, is there a force pushing it upward? And this neglects any air effects, the complications of the world. It's just very simple, the simplest view of this. Is there any force pushing the ball upward as it rises to its peak height? Any questions about the question? How many think that yes, there is a force pushing it upward? How many think no, there's no force pushing it upward? Okay, so the vast majority are going for no, that there's no force pushing upward. And if there's no force pushing upward, why does it continue upward? You tell me. Inertia. So it's true. There is no force pushing it upward, neglecting air. And it moves upward not because something is pushing on it upward, but because it was already moving upward, and that its own nature then is to keep doing what it was doing, namely moving upward. And if it weren't for gravity, it would just keep going in a straight line at a steady pace, in other words, at constant velocity, well, forever or until it hit the ceiling. And if you did this outside, off it would go. Constant velocity. Gravity changes things, but that's the purpose of today. So okay, it's not a very tough question. There is no force, neglecting air, pushing it upward. Why do I keep saying neglecting air? This is a writing questions in general is tricky in physics, because if I try to cover every possible interpretation or consideration, the questions get to be this long and look like legal briefs. So you will find that even on exams, for example, I try to cover everything that's important, but if you really dig deep into the box of possibilities, you might be able to find some crazy exception that messes up my question. In this case, if I don't say neglecting air, there actually is a weak upward force acting on the ball due to air. It's called the buoyant force. It's the topic for 1050, this fall course, and it's what keeps a helium balloon aloft. So this is not a helium balloon, but it's still experiencing a tiny upward force due to the air. So get that out of there. Forget the air effects. There's nothing pushing the ball up. It's going because of inertia. Okay? All right. So some observations about falling balls. When you drop a ball, it begins at rest. And I guess at rest is sort of jargon. It's physics jargon for zero velocity, not moving. Okay? When you drop a ball from rest, it goes faster and faster in the downward direction. It starts not moving, and then it goes faster and faster in the downward direction. And it may not be completely obvious that it goes faster and faster. It just sort of, if you watch it, everything happens so fast, you can't really be sure it doesn't just sort of leap to a certain velocity and then just go with it steadily. But your gut knows that it's going faster, because if things are falling on you, if you've got an opportunity to catch things thrown out of you go to one of those atrium hotels where you're in the middle of the hotel and there are balconies going up for 30 floors, and people are all dropping stuff on you, I don't know, baseballs, you're perfectly happy to go catch the ones that were dropped from the first balcony or second balcony, but the ones that are coming from 40 balconies up, they're a little intimidating because you know they're going faster and faster as they descend. So I can do this in class and sometimes do, but I won't. You know in your gut, the longer a ball has fallen, the faster it's going. All right, when you toss a ball, so this is drop from rest, and that is a falling ball once it leaves your hand, my hand. When you toss a ball up, it doesn't seem quite so much like falling. Is the ball falling on its way up? And I would argue yes, it's a falling ball, even though it's heading in the upward direction. We'll look at that. Its behavior is still the same behavior, apart from the fact that it happens to be heading upward. It's the same behavior as the ball that was dropped from rest. And I'll flesh that out shortly. So it rises, it goes up, particularly if you throw it straight up, it goes up to a certain height, no higher, and then it begins to head downward. And that transition, well, it happens so fast, it's a little hard to know exactly what's going on, but that's part of the job today, is to figure out what happens right there at the top. Once it gets to the top and continues onward, it's falling a lot like somebody dropped it from way up there. So as the ball comes by my hand like this, you can't really tell, on the way down, you can't really, if I don't look up there, and I don't know that I threw it up there, as it comes back down, I'll hit myself on the head if I try to do this, plunk, right? As it passes by me, I can't really tell what its history was, whether it was dropped from somebody up there, or whether somebody down here threw it up and it came back down on its way. Its motion is indistinguishable. So something about that, its behavior once it reaches peak height and continues on is always the same. Doesn't depend on where it was a second or two earlier. And what else? Oh, if you throw the ball not straight up and down, if I don't drop it straight, throw it straight, but instead throw it at an angle, it travels in some sort of arc. And you may well have encountered this arc before. It happens to be a geometric curve known as a parabola. Does that matter? No. But it's basically doing two things at once. It's doing this up and down falling motion at the same time as it's doing a horizontal coasting motion. It's moving steadily horizontally, or its horizontal aspect is just coasting along. But at the same time, its vertical motion is that of a falling object. So that's where we'll go. Anything to talk about before I head in? Okay. Last time a number of you asked questions, which is great, and I have to keep on we have to break the ice every day. So eventually one of you all will ask a question, we'll get the ice broken. Every day. All right, so the 6 questions that I'll go through, more or less, to flesh out the physics of this motion, and they're all how and why questions, my usual harangue that the what, where, whens are boring. They're not science. They're history or other things like that. I wouldn't say they're boring, they're just different. Okay. So why does a dropped ball fall downward? So that's the first big question. It's the great one. And this is Newton trying to figure out, he didn't just watch an apple fall and say, wow, is there such thing as gravity? What he was trying to figure out was, obviously when an apple breaks free of a tree, it falls. And then he would look at the moon and say, is the moon falling? You can't go visit the moon and feel what's going on with it, but is that a falling motion? The same motion that the apple's experiencing? And the answer ultimately is yes. And so that's where the great insight came from. Not that things that are dropped fall. However, it brings up the first force that has a name in it in this class. I've talked about forces generically, that a skater trying to slow down, speed up, or turn will accelerate and therefore needs a force acting on her, a net force, to cause that acceleration. But I didn't sort of say what kind of force. I maybe wave my hands at friction, which is in the future. The first force that I'll really name that we'll pay attention to is the force due to gravity. So this ball, I claim, is experiencing a force called, alternatively, the force due to gravity or its weight. Those are exactly the same idea. The force due to gravity on this ball, which is a whole mouthful, is exactly the same concept as the ball's weight. Okay? And you know the ball experiences weight because if you try to prevent it from falling, you have to push up on it to compensate for something pulling down on it. So right now, the net force on this ball is what? Based on things we talked about last time. Is it accelerating? No, it's velocity 0 and staying 0. So the net force on it has to be 0. So it's experiencing two forces, which is itself an interesting observation. One of them is my hand pushing up. We'll come to how that all happens another day. But the other is that the Earth is exerting a force due to gravity on the ball, or the ball's weight. And I happen to be perfectly canceling the ball's weight. If I stop canceling the ball's weight, watch what happens. It's no longer net force 0. It's experiencing a force. Its weight. So it accelerates. And it accelerates in the direction of its weight, which is a topic I should mention, and I will in a minute. It accelerates in the direction of the force, which is downward, and it goes from velocity 0 to more and more and more, bigger and bigger downward velocity, faster and faster. Speed picks up, always, in this case, always in the downward direction. A little about the direction issue. When I introduced Newton's second law last time, I told you that a force causes acceleration, and I said that the acceleration of, say, the ball is exactly equal to, that's the effect. The cause is the force on the ball, and the resistance to the cause is the mass of the ball. So how much the ball accelerates is the force exerted on it divided by the ball's mass. Familiar? I hope. What I forgot to say last time is there's a direction aspect to both sides of that relationship. Acceleration occurs in a direction. You can accelerate to your right. This is acceleration to the right. Stop. And this is acceleration to the left. They are caused by forces of equal strength. They happen to be exerted by the floor. They happen to be in opposite directions, though. In this case, the force that was exerted on me with the help of the floor, or by the floor, was toward the right, and I accelerated toward the right. In their case, the force exerted on me was to the left, and I accelerated to the left. So in this case, the ball experiences a weight force downward. And it accelerates downward. Technically, toward the center of the Earth. Or even more technically, the Earth has a point, a conceptual point about which all of its mass is centered. Do I want to use center of mass and gravity are tricky to disentangle in this context. But there's the center of the Earth. There are a couple of concepts that live at the center of the Earth, and one of them is a center of mass, and one of them is a center of gravity. In any case, the ball is pulled toward that center. And so, obviously, if I drop the ball here, it goes that way. If you took me off to Australia without reorienting me at all, I would be down there, still visible to you. The ground would be above my head, because I would be on the other side of the Earth, right? Still oriented as I am. And if I dropped the ball, it would go toward the ground, because the center of the Earth would be above me now. Can you visualize that, or is that just randomly confusing? Gobbledygook. All right. So, every object, it turns out, on the surface of the Earth, near the surface of the Earth, experiences its own weight, its own force due to gravity. And what else about those things? If that's all they experience, objects experience only that force, then they're not experiencing net force 0. And an object that is not experiencing net force 0 is not covered by Newton's first law, the law that says that objects that are free of external forces move at constant velocity. Instead, it's covered by Newton's second law, relating the net force on something to its acceleration. It's going to accelerate. So everything in this room, if we take away any other forces acting on them, for example, if we removed your chairs and the floor, you would all begin to accelerate downward toward the center of the Earth because you have weights. All right? So we've got the reason why objects fall. They fall, and let me just beat on it one more second with falling. The whole concept of falling is an object is falling when it's experiencing one and only one force. Its weight. When it's free of all other forces and experiencing only its weight, it accelerates downward due to that weight, and we call that falling. And that, I can get a little ahead of myself by pointing out that whenever the ball is not being supported by me and the air isn't doing much, it's experiencing its weight and only its weight and accelerates downward. It doesn't matter which way the ball is moving. It still experiences its weight and still accelerates downward. That seems pretty straightforward when I drop the ball from motionlessness, from rest. But what about when I throw it up? On its way up. Yeah, it's moving up, but which way is the force acting on it? You show me with your hands. Down. Which way is it accelerating? Down. Not down. It's moving upward, but it's accelerating downward the whole time on the way up. That's why it slows down. Remember me doing my human animation stuff, talking about acceleration can be opposite velocity, and I was doing it horizontally. So I was moving to the right, but accelerating to the left. Right? That little trick? Well, if I could do it on the wall, if this were a movie, and an animation, I would do the same trick on the wall. So this is high, that's low. So here I am. I'm going higher and higher and higher and higher. Coming to a stop. And now I'm going lower and lower and lower and lower. Can you mentally rotate it like that? In that case, it's just like the ball. The ball's going higher and higher and higher, lower and lower and lower. And as it's going higher, it's accelerating toward lower and slowing down. So I've told you the whole story practically. Now I just have to rehash it. All right. Important observation about falling motion is, what if I drop two completely different balls? Okay. Is one of these going to fall, whatever that means, faster than the other? Basically, or which one's going to hit the floor first? What do you think when I drop them simultaneously from the same height? Take your vote. Think about it for a second. Ready, get set. Exactly the same moment. I heard only one smack. Try a different ball pair. I'll do this trio. Ready, get set. All together. Some days do it. I could get up on the bench and jump with the balls, and I'll hit the ground at the same time, break my ankle. That'll end the fun. So I won't do it. But because I'm usually like staring at this, and I fail to anticipate when the floor hits me. So the observation is an interesting one, that all the balls fall together. There's no difference between them, which means what? It means that they accelerate downward at the same rate. They start from rest, no movement, velocity 0, that's rest. And they accelerate downward, which means that their velocity increases in the downward direction at a certain rate. Faster, they pick up speed, they pick up speed, they pick up speed. And amazingly enough, they pick up speed at exactly the same rate. Whether it's a basketball or a baseball or a tennis ball or any of them, they all go together. Neglecting air effects, they just all go together. So how is that possible? I hope that you accept the fact that that's true. That the more mass, if I drop the bowling ball, I won't do it. I mean, it falls from the table once in a while, and the people downstairs don't appreciate it. It's like, oh my gosh, earthquake. So, but I'll do a little version. Ready? Together. It doesn't matter whether it's a baseball, bowling ball, whatever. But the baseball has so much less mass than the bowling ball. And with less mass, it's easier to shake. Remember the idea that mass is the difficulty an object has in shaking. This baseball, easy to shake. This bowling ball, not so easy to shake. In fact, as I shake it, you'll notice I'm shaking too. As I push it away from me, it pushes me away. Back and forth. This is related to action and reaction, what's known as Newton's third law, which we'll come to. But if I'm pushing on it, it's pushing back on me, and its mass is not that different from mine. Consequently, I accelerate. It shakes me while I shake it. So this little guy's got not very much mass. It ought to be able to accelerate like crazy and hit the ground way before the bowling ball. Right? There's a difference, though, between these two balls other than their mass. The bowling ball has not only more mass than the baseball, it also has more weight. And therefore, it's pulled down harder by the gravity. So yeah, it's harder for gravity to make this guy accelerate. But gravity's up to it and pulls harder on it and makes it accelerate anyway. And they accelerate together, exactly the same rate. So I can now flesh that out with as I've gotten in the view graph here, that if you take any one of these balls, put its weight up on top of a division, and you put the mass of that same ball on the bottom, so the numerator and denominator, and divide one by the other, strangely enough, they all come out with the same value. The weight of any ball divided by the mass of that same ball is always 9.8 newtons per kilogram. Remember, newton's the unit of force, kilogram's the unit of mass. And that's 9.8 approximately. It actually depends on where you're located on Earth. This is a value here near the surface of the Earth. It's actually a little bit less than that in Charlottesville. It varies. In fact, it varies from location to location for real. It's the closer you are to the center of the Earth, the stronger gravity becomes. If you drill holes in the Earth, it gets more complicated because now you've got some of the Earth is above you, and gravity from that portion above you is pulling you up, not down. But as long as you stay sort of above the Earth, the closer you get to its center, the stronger gravity gets. And you might think, well, how can you do that? Well, if you go into the Blue Ridge, where you're farther from the center of the Earth, you actually are experiencing slightly weaker gravity, and your weight decreases a tiny bit. Not so much. But if you go to, for example, the equator, the Earth, because the Earth is spinning, is not a perfect sphere, regardless of what they told you. It's obviously not flat, but it's flung outward at the middle. It's a little bit wider around its equator than it is top to bottom or pole to pole. And as a result, when you go to the equator, your weight, the strength of the force due to gravity on you, decreases for real by 0.5% as compared to what your weight would be if you were on one of the poles. It's a measurable amount. So you can indeed lose weight by going on a trip to Ecuador. Okay? It's real. I lost weight. The point is that measurement by weight is not the perfect measurement and should be taken with a little bit of a grain of salt. Okay? So, anyway, the strength of gravity near Charlottesville is pretty close to 9.8. It's a little less. Depends on place to place. This affects, what is this? It does affect real things like adjustments for scales. Some of the scales, they will read your local weight, and that will depend on where you are. All right, so it turns out every kilogram of mass here in Charlottesville weighs about 9.8 newtons. And if you have two objects, one 100 times as much mass, well, the one with 100 times as much mass also has 100 times as much weight. They go together. That relationship where mass and weight are exactly proportional to one another it turns out it's a remarkable relationship, that it didn't have to be that way. The fact that it is that way, that you double the mass of something, you also double its weight, is a remarkable observation, and it set Einstein thinking. He wasn't the only person thinking about this, but in about I'm a poor historian of science. I'm saying it's in 1912, 13. The general theory of relativity is based on the observation that weight and acceleration and mass are all linked together. And that gravity basically has to do with acceleration. Way beyond this course, though. Okay, so just to make you think for a moment about mass and weight. You've got the idea that mass is how hard it is to shake something, or how hard it is to make it accelerate. And you measure that by, you want to know the mass of the puppy? Shake it. Whoa, hard to shake, therefore lots of mass. Weight is a gravity story, and it has to do with how hard the local gravity pulls down on it. And to do that, the simplest approach is simply to see how hard it is to support it. Whoa, gravity's pulled out hard because I have to push up hard to achieve net force 0 and no acceleration. So it's a simple question then. A US quarter, a US dime, I've got it. Compare their weights, compare their masses. And so how many think, okay, the question, basic idea. How many think that a quarter has the same mass and the same weight as a dime? Okay. How many think a quarter has the same mass but more weight than a dime? How many think a quarter has more mass but the same weight as a dime? You're all waiting. A quarter has more mass and more weight than a dime. Yay! Okay. Yeah, but they are different. They're good. Simple question. But they're different measurements. I'll just say one of the first, when I was first writing the How Things Work book, and I was looking at other people's books just sort of see how they laid them out. There was a book that talked about measuring mass, and it had this picture of a bunch of, what's it called, a sedan chair with a grossly overweight potentate in the sedan chair. And these guys the people were carrying it, and while this potentate was enjoying the luxury, and it was saying, this is how you measure mass. I'm thinking, no, that's how you measure weight. You smash the poor carriers. To do mass, you shake the potentate. You probably won't live long enough to enjoy it, but better measurement. Okay, so about the falling process then. So the observation so far is, this is one of the rare occasions when I've got a view graph with equations on it. 3 of them, maybe even more if you count the equal signs. So every kilogram of mass on the Earth weighs 9.8 newtons. What can you do with that? Well, if you just write out Newton's second law, remember Newton's second law, for a ball, it is, the effect is acceleration of the ball, and the cause is the net force on the ball, and the resistance to that force is the mass of the ball. So this is just Newton's second law, pointing out that if you exert a certain net force on the ball, it's going to accelerate, and the acceleration will be the net force divided by the mass of the ball. So far, so good? All right. The only force acting on a falling ball, I mean, right now this is generic. It's just any old force on the ball. You could be pushing on it. This equation works. What if we let go of all forces except for weight? Let only the weight of the ball act on it. In that case, the ball has a new name. It's a falling ball. That's just special. And instead of having generic net force on the ball, we'll have the weight of the ball. So this is just Newton's, so far here, this is just Newton's second law for the special case of a ball that's experiencing only its weight and is therefore a falling ball. All right? Well, the weight of the ball divided by the mass of the ball, we already know what that relationship is. That was in the previous view graph. Whenever you have the weight of anything divided by the mass of that same thing, it's always 9.8 newtons per kilogram. That's just how much weight weight divided by mass. It's always 9.8 newtons per kilogram here near the surface of the Earth. So those are two equalities. Newton's second law on the left, and then this relationship between weight and mass on the right. Well, we can skip the thing in the middle and just go, the acceleration of a falling ball is 9.8 newtons per kilogram. That's weird. So here it is down below. It's acceleration, well, it's got a new name now. It's called the acceleration due to gravity instead of the acceleration of the falling ball. It's just 9.8 newtons per kilogram. Well, if you remember the first day I talked about, well, the second day, I guess, last time, Friday, I talked about the Newton being it's the unit of force, and it's related to other units by Newton's second law, really. The Newton isn't a fundamental physical quantity the way the second is, or the meter is. The Newton is built of the other units. It actually has, what is it? I should know. Is it a kilogram meter per second? Kilogram meter per second. Oh my gosh, I'm rusty. It's built out of the other units. And if you rearrange the units of newtons per kilogram, they can take another form. They are equivalent to meters per second squared. The observation then is, when you combine these two equations, the relationship between a force on a ball and the acceleration of the ball, with mass included, and the relationship between weight and mass here on the Earth's surface, you end up with an acceleration that's equal to 9.8 meters per second squared. That's known as the acceleration due to gravity. It's the acceleration in which everything accelerates when it's experiencing only its weight. So if all these equations are just in your mind, which is fine. Well, I mean, ideally it would be less than fine, but you know, if you can't follow the calculation, don't worry. The observation is simple. Near the surface of the Earth, every falling object accelerates downwards steadily at 9.8 meters per second squared. Its velocity changes at the same steady rate in the downward direction, because it's downward force, whether it's a ball, whether it's a diver jumping off the high board, whatever. They all go down together. That is why this observation works. Ready, get set. They all go together. Doesn't matter what the masses were, they're different. Doesn't matter what the weights are, they're different. But the relationship, the ratios of weight to mass are the same. Therefore, the acceleration, the same. Questions about that? It's a pretty useful and important observation. So if you've lost it, ask me. Okay. So, if you drop a handful of coins in a wishing well, which coins hit first? So you drop them all from rest, say, to make life as simple as possible. You think the heaviest coins hit first, the lightest coin, medium next, lightest, they all hit together. Yeah, they all hit together. So if I take the whole basket of balls, so they all go together. And it's because they all accelerate at the same downward rate of 9.8 meters per second squared, and I get to play pickup. All right. I filmed for an online version of this course, a small one on Coursera, one of these massive open online classes. I decided to film stuff out the back window of the third floor of this building onto the grass below, and including the bowling ball, which was a lot of fun. And so for about a year after doing that, it's about 3 years ago, but for a year after that, there were these round dents in the grass out there. They've since finally sort of gone away. But one of the things I had most fun doing was throwing not only the balls out the window, but the camera filming them. No, okay, didn't actually throw it out. It was one of these GoPro Heroes. I let it ride down on some strings, straight down. But I dropped everything together, and from the perspective of this falling camera, which falls at the same rate as the balls fall, they all go together. And so the view out of the camera was the cluster of balls, and they all go down together, and they just hover in the middle of your view while the world comes up at you. So it worked out great, but anyway, I should resurrect it for the class sometime. Maybe I'll go find it. What? Please go. There you are. So, having shown you that everything falls together, then I can pull out this sheet of paper and go, oops. What went wrong? Right? You know air resistance. If I could get rid of air resistance, would they fall together? Right. Can you think of a way to get rid of air resistance? on the sheet of paper? Folding will be fine. I won't do the folding. Instead, I'm going to let it chase a book. They are not attached to one another. So there's nothing the book does that forces the paper to stay with it. Instead, it gets the air out of the way. So it will eliminate air resistance for the paper. You can follow the idea? They hit together. And that idea of following a moving object to get the air out of the way, that's the concept of drafting, which shows up in a lot of sports, racing sports. If you're having trouble getting through, dealing with the air in front of you, boy, it's all of them. It's certainly bicycling. It's a huge thing in cycling. It's in skating. Those of you who do any of these sports, you know that if you can get into the wake behind whatever it is moving ahead of you, where they've already pulled the air with them, you get rid of that air resistance, and suddenly it's a whole lot easier. Well, it's relatively easier to move. Yeah. Is it the same thing in water? Yes. And so anytime you get water's worse. So in water, you got tremendous water resistance to deal with. And so if you drag the water with you, and someone else is following you in your wake, they've got an advantage. And I think that's one of the reasons why they have, one of the reasons for the lane markers in, say, a swimming meet, is to try to control the flow of water that you leave behind you so the people in the other lanes don't have an advantage. Other questions? All right. So would a ball fall differently on the moon? And the answer is yes. It would fall more slowly. In going to the moon, what changes? Has the ball's mass changed? How many think yes, the ball's mass has changed in going to the moon? How many think no, the ball's mass has not changed in going to the moon? Great. Yeah, the ball's mass has nothing to do with gravity and location. The ball is just as hard to shake on Earth as it is on the moon, as it is out in deep space. Mass is the same. What has changed in going to the moon, though, is the strength of gravity. It's about 1/6 as large on the moon as it is on Earth. That's the trade-off of two different effects. On one hand, the moon has a lot less mass of its own. It's about 1/100th of the mass of the Earth. And as a result, its gravity is just much weaker. If you go to a certain distance from the Earth, actually from the center of the Earth, and a certain distance from the center of the moon, the gravity, strength of gravity is different by about a factor of 100. Because it turns out mass ultimately gives rise to gravity. The Earth's mass is responsible for the Earth's gravity. And the moon, having only 100th as much, has only 100th of the overall gravity. On the other hand, the moon is so much smaller, you're closer to its center. And that compensates to some substantial extent. So the gravity on the moon isn't down by a factor of 100 when you're on its surface. It's down by about a factor of 6. The result then is that the acceleration due to gravity on the moon is about 1.6 meters per second. So if we could go there and drop, ooh, we're on the moon, and we drop it, it would pick up speed much more slowly. And other things would be present too, like if you jumped upward, so we'll see, as you jump upward, you become a falling object as soon as you leave the ground, and you begin to fall, to accelerate downward. But if that acceleration is much weaker, as it is on the moon than it is on the Earth, you don't come to a stop as quickly. The Earth is pulling down hard on you as you go up, and it brings you a stop pretty quickly, and down you come then. On the moon, not so quickly, and you can jump higher. And I guess was the death of the last of the Apollo astronaut Cernan recently. Before your time, right? The Apollo was a great thing of my years, like now. For you guys, and one of the interesting events, one of the astronauts was a golfer, an avid golfer. I'm not sure which one anymore. Anyway, he took his golf balls and a driver or something like that to the moon and hit golf balls, and they would just go out of sight because golf balls, particularly in the absence of air, which is a big deal for golf balls. But to get rid of the air, they travel in the motion of a falling object, and they were falling slower, so they would just go off they go. And so somewhere up there, far from one of those Tranquility Bay or the sites of landing, there's some golf balls in the rough. Okay? Okay, so having said all this about falling balls, the notion that they're accelerating downward and they go faster and faster downward direction. So how do you actually track the various physical quantities for a ball as it falls? And the various physical quantities I have in mind are its position, its velocity, and its acceleration. Those three are they're related quantities. Remember, position is where an object's located. Velocity is how the object's position is changing with time, specifically the rate at which it's changing with time. And acceleration is the rate at which the object's velocity is changing with time. So they all go together, but they're different quantities, but they're all connected. And it turns out when you drop a ball from rest, life is pretty simple. So this is one version of the drawing that's in the book. It's now an animation in the book. So when you drop it from rest at the moment of letting go, which I called 0 seconds, time 0. As soon as you let go, the ball has a position which we'll just for simplicity we'll call position 0, the starting point, the reference. And the velocity, since it wasn't moving, is 0. 0 in any unit, in this case meters per second, to make it like metric. What does become non-zero the instant you let go of the ball, however, is its acceleration. It's now experiencing only one force, its weight. So it's immediately accelerating downward at 9.8 meters per second. And the question came up last time, I think, about pluses and minuses in the world of these physical quantities. When you're moving to the right, how does that relate to moving to the left and positive and negative? For a motion that's vertical, this is just reminding you of the story a little. I will say, anyway. For motion in one direction, along one dimension, instead of pulling out the whole machinery of the world of vectors, this direction, that direction, this direction, we can go to a simplification where if we're working only along one direction, for example, vertical, we can simplify the world by just saying, that's the positive, those are the positive positions up there. Here's 0, and those are the negative positions below it. So that's what I've done over here in this drawing, is I've referred to up and down as positive being up, negative being down, and therefore the acceleration, the minute you let go of the ball, is the acceleration due to gravity. That's its name, the acceleration due to gravity. And it's about 9.8 meters per second squared downward, which in this case is in the negative direction in this simple one-dimensional story. You okay with minus sign being downward, positive sign being upward? No questions about it? So the point is, the instant you let go of the ball, its position is still 0, its velocity hasn't changed, it's still 0, but it's accelerating downward. Things are going to change starting now. And after 1 second of falling, always at this steady downward acceleration, 9.8 meters per second squared, the ball's moving. It's moving pretty fast. In fact, the fact that its acceleration was 9.8 meters per second squared means that in 1 second it will accumulate an entire 9.8 meters per second worth of downward velocity. And that's the case here. After 1 second of falling, it has gone faster and faster and faster, and because the rate at which it's increasing its downward velocity is 9.8 meters per second squared, it will get to 9.8 meters per second after a second. After 2 seconds, it will be going twice that fast. After 3 seconds, 3 times that fast. That's what acceleration means. Your velocity keeps changing, in this case steadily, because the acceleration is steady. It's constant. Constant acceleration gives a steady change in velocity. In this case, always downward, always faster. Okay? Questions? All right. So during the first 3 seconds of fall, which is what I've got up here on this story, the acceleration is 9.8 meters per second squared downward and never changing. Why? Because it's always caused by gravity. And the weight of the ball doesn't change. The mass of the ball doesn't change. The acceleration due to gravity doesn't change. It's steady downward acceleration. But that doesn't mean its velocity is steady. In fact, it means its velocity isn't steady because it's continuously picking up downward speed. So it goes from motionless to down 9.8 meters per second downward to twice that to 3 times that. All right? Any questions about acceleration and velocity part? The last part to deal with is the position. The position, as you'll notice here for that falling ball, changes in a more exotic way. The ball drops about 5 meters in the first second. It drops an additional 15 meters in the second second. And it drops an additional 25 meters in the third second. It's covering bigger and bigger distances each second. It's going, the steps it's taking, going downward, are getting bigger and bigger. Well, it's because it's going faster. And this means that when you drop something, for example, a bungee jumping, suppose you open up a bungee jumping concession, and you want people to fall for 1 second. So they step off the platform and fall for 1 second. Well, in 1 second, they'll start the second at 0, not moving, 0 velocity. And they'll finish the second having accumulated an entire 9.8 meters per second squared downward, meters per second downward. Their average speed during that first second then was only halfway in between those two, 0 and about 10. It's about 5. They were traveling downward on average about 5 meters per second. They don't fall very far. They only fall about 5 meters. That's this number here. So bungee jumping, if you had a 1 second fall bungee jump, it would only have to be about 5 meters tall plus some room for them to slow down and come to a stop. So you could almost fit it in this room. For a 2 second bungee jumping adventure, because they have longer to fall, they will at the end of the fall, they will be going faster. So their average downward speed over the course of this entire 2 second fall will be bigger. They'll travel not just 5 meters or not just twice that. They'll travel 4 times that. If they make a 3 second bungee jumping adventure, it's yet even more. Where am I going with this? Public service announcement. If you try to set up bungee jumping and you want, a 2 second, 3 second fall, fine, you can do this. The 4 and 5 and 6 second fall, they travel so far, you can't do it. So things like, where have you seen this? At the amusement parks, the drop towers, drop of death or whatever they're called. What's the one at King's Dominion? Tower of Doom or something. Anyway, they drop you for about 2 seconds, which is the coincidence of 2 numbers. It's about as far as they can drop you with a reasonable sized tower. If they try to go for 3 seconds, it gets too tall. The other thing is about 2 seconds is about all most people like me can tolerate before it's like we go like, that's too long. Okay, 2 seconds of sheer terror is enough. All right, so what do I leave you with at this point? Is that objects drop from rest go faster and faster. Their acceleration is steady, but their velocity is increasing. They're going faster and faster and covering more distance with each passing second. So their height drops by ever increasing steps each second. And I'll finish up this falling story on Wednesday.